handed out the new handout, but we'll do some other problems off the old handout first, the previous handout first, before we do that. Homework I just gave you is not due till a week from Thursday. So I'm going to go ahead and give it to you now. That'll be the last homework before break, obviously. That's a week from Thursday. All right. Also, just to make a quick announcement, if you want to mark your calendars for a week from Thursday, Friday is Pi Day, but since that's the day before spring break, figured somebody might stick around for Pi Day. So Pi Day, Thursday, we're going to have pie last week. So I bought 10 pies. So we're going to have pie last week, Thursday afternoon. So I'll remind again, it'll be around like 1:45-ish on Thursday. But my guess is there'll be plenty of pie for later in the afternoon too. So please stop by and get pie. Lots of different flavors. So we'll also have a little thing set up in the UC too earlier in the day. But just thought I want to make sure, mark your calendars for our early Pi Day celebration. Or bad rounding Pi Day celebration. Okay. All right. Any questions at all over anything before we get going? Things are going okay? Yeah. All right. Also, our next exam, I think, is April 1st, if I remember right. I think that's what I told you yesterday, isn't it? Yeah. So, still got a little bit of time. It'll be after break. So if you're worried about having an exam before break, we don't have one before break. It'll be after. So I'm guessing you probably already have some other exams before break anyway. So, all right. Anyway, last time we were talking about negative binomial PMF. It's kind of related to the geometric. So we've got lots of different problems that kind of start with the same setup. You've got successes and failures to start up. But, for example, binomial counts number of successes at a certain number of trials. Geometric counts number of trials until the first success, right? And then negative binomial extends that. Negative binomial extends it to the number of trials until the rth success, whatever r happens to be. So it could be second, it could be third, it could be 12th, or what have you. So that was the PMF we created last time. But what we did not do is actually verify that it is a PMF, and we did not do any of the other important information about it. We didn't find its mean, or its variance, or its moment generating function, but of course it's on the sheet that I gave you before, right? So but let's talk about how we get to it. In particular, it's a good reminder of Taylor series. I know you all loved series when you took calculus. This is probably your favorite topic in calculus. No? Well, it's mine. So, but I'm weird. It's fine. All right. So, remind what in particular we're going to do Maclaurin series. So, remember Maclaurin series is just Taylor series centered at 0. So, remember when we have a Maclaurin series, we do the nth derivative, we evaluate it at 0, we divide that by n factorial, and then you multiply by x to the n. That is the Maclaurin series for f. Hopefully those are equal. We remember, hopefully, that there are 3 possibilities for conversion to the power series. One's really bad, one's really good, and the other one's okay. So remember the 3 possibilities are the only place where the series converges is at the center. In this case, it's centered at 0. So if I plug in 0, I get whatever out, whatever the constant term is. But it doesn't converge anywhere else, meaning that if you plug in anything else but 0, the series will go off to infinity, or it's a diverge. That's the bad case. The good case is that the series converges no matter what you plug into it. And you had some good examples of those. E to the x, and we'll revisit e to the x's Maclaurin series later today. Sine of x, cosine of x, those all had Maclaurin series that converged everywhere. Then you have the middle case, right? There's some sort of a region around the center that it converges for everything inside that region and diverges for everything outside that region. The geometric series, the 1 over 1 minus x, that's an example of one of those because it only converges if your x is between -1 and 1. That's an example of those. The Maclaurin series that you learned in calculus for inverse tangent and for natural log of 1 plus x also are examples of those. In any event, I just wanted to give a little bit of a reminder because it's probably been a minute or two since you've thought about Maclaurin series. Okay? I'm not worried necessarily. We'll see that it will converge, but I'm not worried as much about convergence. Is this using it to prove some properties that we need? In particular, we're going to use the Maclaurin series for a particular function to show that this really is a PMF. And we're going to use the Maclaurin series for a particular function to find the moment generating function for this for a negative binomial random variable, and then use that to find the mean and the variance, or show what they are. Okay. All right, so which function am I going to use? Well, here's the function that we're going to look at. I'm going to look at f of x equals 1 minus x raised to the negative r. And this is where the negative binomial comes from, the name comes from. Binomial, because I've got a 1 minus x inside the parentheses. Negative binomial, because I got a negative exponent. So that's where the negative binomial comes from. Okay. So the binomial random variable comes from that binomial theorem, right? Talk about how the binomial theorem expands into your x plus y to the nth power, and we see those binomial coefficients that come out. Okay. Same kind of concept here. But what we're going to do in this case is let's find the Maclaurin series. Remember, for your Maclaurin series, I need to take n derivatives, right? And see if we can recognize a pattern. Okay. So first derivative here, you're going to bring your negative r down in front, but you're also going to multiply by a -1, right? You do the chain rule. So you get a positive r, 1 minus x to the negative, and I'm going to write it as r plus 1, factor out a negative sign. Right? Bring your power down in front, decrease the power by 1. But I also have a chain rule, so I have a -1 that'll get multiplied by the inside there. I'm going through it quickly because I don't want to get bogged down on the derivation. Okay. All right. Second derivative, same idea. I'll bring the exponent down in front. It'll have a negative, but the negative will cancel out because of the derivative of the inside, the chain rule, right? So you'll get in r times r plus 1, 1 minus x to the negative, and again, I'll factor it out, being r plus 2. We agree? I'll do one more, and then I think we'll probably recognize the pattern. R double prime. Again, bring your power down in front. I probably should really put it all the way in front because I'm kind of writing it weirdly. Bring your power down in front. It'll have a negative, but again, with the chain rule, the negative will cancel. 1 minus x to the negative r plus 3. We agree? Yes. I'm subtracting 1, but I'm factoring out the negative. So it's a negative r minus 1, but I'm factoring out the negative. So that's why I have a negative of r plus 1, and then I do the same thing all down. Okay. All right, so we can probably see what the nth derivative is then. That was a third derivative, wasn't it? That I just did. So notice with your nth derivative, I forgot to put my of x here. Notice that the first derivative just had a single r there, right? A 0. Second derivative had an r and an r plus 1. Third derivative had an r and r plus 1, r2 plus 2. So this number here is always 1 less than that one. Right? And then we'll have 1 minus x to the negative of, r plus n here. All right, so those are, do we agree that that's the nth derivative? Okay. Now remember, when you do your Maclaurin series, I don't use it with the x in here, right? I put 0 in there, correct? So when you do the nth derivative evaluated at 0, what's this part right here going to equal? That'll be a 1, right? Because you'll get 1 minus 0, you get a 1 to a power, right? So this is just going to be, and I'll write it this way. I'll actually flip it around this time. R plus n minus 1, R plus n minus 2, times, R plus 1 times an R. Reminds you of a factorial, doesn't it? Doesn't go all the way down to 1, but it should remind you of a factorial. So now let's plug it into our formula for the Maclaurin series. So 0 to infinity, R plus n minus 1, R plus n minus 2, all the way down to R plus 1 times R over n factorial, and then x to the n here, right? Yes. What happened to the 1 minus 0 I plugged in 0? What's 1 minus 0? Right, that's right. Well, 1 to any power is what? 1 to any power is just a 1. It's just a 1, right? That's what happened to it. It's just a 1. All right. How many factors are here? How many factors are in that product? There's n of them in that product, right? Starts at r plus 0 and goes to r plus n minus 1, right? There's n factors in that product, and notice I also have an n factorial here, don't I? Okay. Notice that what's missing? If this were a factorial on the top, what's been canceled off? So if this were all the way down to a factorial, what's missing on the end here? R minus 1, R minus 2, all the way down to 1, or R minus 1 factorial, right? We agree? Okay. So I can rewrite this as R plus n minus 1 factorial over n factorial R minus 1 factorial x to the n. Right? I did. It's in here. There's an R minus 1 factorial in here. In the numerator too, right? It's missing here, isn't it? There's a missing R minus 1 factorial there, isn't there? It doesn't go all the way down to 1. Right? It's missing. So I put it in on top and made it a factorial, but I also had to divide by it. So it kept everything equal. Now, what if I write this in a strange way? What if I write that n factorial as r plus n minus 1 minus r minus 1 factorial? I know you don't have to rewrite it that way, but what if I write it that way? Why did I write it that way? What do I recognize that as now? My drawing tools are gone. It's a combination, isn't it? Here's r minus 1, r plus n minus 1. Choose r minus 1, isn't it? You see it? So this is r plus n minus 1, choose r minus 1, x to the n. That was fun. Okay. So this is your Maclaurin series for the negative binomial, if you will. This is your, now the whole reason why I did this is so that we can show that it's a PMF and find its moment generating function. I'm not going to make you reproduce all of this stuff, but it is a good review of Maclaurin series. Okay. And since you don't see them very often outside of when you do calculus, except for IfEQ, you see it in DiffEQ, okay? But other than that, you don't really see it. So I want to show you that, no, these really do exist in nature, they exist in nature, and we actually do use them in other areas. Okay, so, but I do want to use this. Okay, you can show that this has a radius of convergence of 1, so it'll converge from -1 to 1. It will not converge at -1, but it should converge at 1. So it'll converge at the right endpoint, but not the left, and I'm not worried about that either. Okay. All right, so how do we use this? Whew, that was a lot of work, wasn't it? Okay, let's go back over to our negative binomial PMF. It kind of looks like that, does it? Not everything, but this part kind of looks like it, doesn't it? A little bit, all right? So in this case, if I want to show it's a PMF, I need to show in particular that this adds up to 1, right? If I add it up over the support. So if I do the sum from x equals r to infinity of x minus 1, choose r minus 1, 1 minus p to the x minus r, p to the r. What's our index? What are we indexing? Summing over? What values are the ones that are changing? What values change when we do the sum? X, right? So in particular, what can I do with that p to the r? Put it in front, right? I can factor it out, right? So I can take that p to the r, perhaps I can take that p to the r, and move it out in front. All right. There's a reason why I went through the Maclaurin series, right? Otherwise, that was a really bad introduction to this. Which I'm not saying I don't do bad introductions to things. I'm just saying that would have really sucked. I just tortured you for 10 minutes for nothing. I mean, it was fun for me, but maybe not so much fun for you. All right. So again, we just came up with this Maclaurin series, right? Oops, r minus 1. We came up with that, didn't we? This series starts at 0. So what would I need to do if I want this series to start at 0? So I want to start my index down r. What do I have to do on the inside? Add r everywhere, right? So then I get r plus x minus 1. Choose r minus 1. When I add r in here, notice I just get 1 minus p to the x when we reindex, right? If I'm going to start my index r units lower, I've got to up my x's by r units to keep everything equal. I got to balance it, don't I? Does this look like that? Rather than using an n, I've got an x, but does this look like that? What's been plugged in for x up there? 1 minus p, right? So this is equal to 1 minus p to the negative r. Right? Because I've taken the 1 minus p and plugged it in for the x right here. Right? I know my n's and x's are flipped around, right? Okay. My x is playing the role of n, and my 1 minus p is playing the role of x, right? 1 minus, the quantity 1 minus p is just p. I got p to the r times p to the negative r. What's that equal? 1, which is what I needed to equal. That was why I went through the Maclaurin series. That was not bad, right? This part's not bad. It took me 3 steps. How's it 1? What's p to the r times p to the negative r? What do you do with your exponents? Add them, so I get p to the 0. P to the 0 is 1. That's how it's 1. All right, so let's do the moment generating function so that we can do the mean and the variance. How do we what's the definition of moment generating function again? Expected value of what? E to the tx, right? That's our definition. Pardon me. So we'll do e to the tx times our PMF. And now we'll do the exact same thing we just did. Reindex. Oops, I forgot my P, didn't I? Let's reindex. So you should have an e to the t times x plus r. The r plus x minus 1, choose r minus 1 is just like what we had before. 1 minus p to the x, and then a p to the r. Now, remember when we did this for the PMF, we pulled out a p to the r. What else can we pull out of the PMF? We have to do something a little about algebraic. But what else can you pull out of the PMF? What else can you have in there that doesn't have any x's in it? E to the tr, right? If I distribute the t through and split it up with the plus sign as multiplication, I've got an e to the tr, right? So we can pull out a p to the r and an e to the tr. And on the inside, we'll have r plus x minus 1, choose r minus 1, 1 minus p to the x, and e to the tx. Oops, that's a times sign, not an equal sign.
Does that bump up the average for question 1?
Say that again? Oh, yes, it does bump up the average in question 1. Exactly. On average, your instructor makes so many mistakes per class period. I make a few. It's okay. I'm glad you caught that. It's hilarious. All right. I can do something similar on the inside and on the outside with an exponent. On the outside, what can you do with that r? Relative to these two terms, what can you do with the r? Yeah, well, it's p to the t and then all to the r, right? Can you do the exact same thing on the inside? Oops, not pet. P to the t to the r. Can you do the exact same thing on the inside? I got an x on both of them, don't I? So I can write that as, put the e to the t in front. Take e to the t times 1 minus p to the x. Now look at that summation down here in the lower right and compare it to the summation that we did up in the upper left. It's almost identical, right? Instead of having a 1 minus p on the inside, we've got e to the t times 1 minus p on the inside, don't we? So this is going to be Pe to the t to the r times 1 minus e to the t times 1 minus p to the negative r. Because we're just plugging into for the function. That's the Maclaurin series for 1 minus x to the negative r. And then we will put everything together this way and raise everything to the r power, right, as the final fraction there. Now, one reason why I wrote it this way, without the r power on it, this moment generating function should look familiar. It's the same moment generating function for the geometric. Remember, what is geometric counting in? Number of trials until the first success. If r is representing the number of successes, that makes sense, doesn't it? Okay. So it's not a huge surprise, and we're going to talk more about this later in the semester. It's not a huge surprise that this moment generating function has similar characteristics to the geometric one. What also isn't going to be a huge surprise is when we do the mean and the variance here in a second. Okay, so let's do mean and variance. We have moment generating function. Oops. 1 minus e to the t to the times 1 minus p, all raised to the r. Remember, for moment generating function, we can take the derivative, plug in 0, get the mean. Take the second derivative, plug in 0, get e of x squared. But it might be a little bit easier, given the fact that I've got this quotient and then a big power, it might be easier to do the log. Remember that trick we did? Take the log of it and then take the derivative? Remember doing that? Okay. Why would I want to take a log here? What can I do with the exponent? Bring it down in front, right? Log of a quotient is the same thing as what? Log of a difference. And then I've got a product on top, which I can also split up, right? So on top, I would have natural log of p plus natural log of e to the t. What's natural log of e to the t equal to? T, right? And then we would have minus, I can't split up anything on the bottom, unfortunately. I'm stuck with that. That's the minus the bottom, right? So natural log of the top is what this is. This is natural log of the bottom, which I can't split up because I got a minus sign in the middle. So that's as good as that gets. But this is nice, right? Especially when you take the first derivative, right? Derivative with respect to t. What's the derivative of natural log of p with respect to t? 0. It's just a constant, right? Derivative of t? 1. Now the other one's going to require a little bit of chain rule work, right? I got to do 1 over the inside times the derivative of the inside. But the derivative of the inside isn't horrible. It's a negative e to the t times a constant. Well, the derivative is going to be itself, isn't it? This is going to be a negative e to the t times 1 minus p. That wasn't terrible. Right? 1 minus p is just a constant. Derivative of e to the t is e to the t. Minus a minus here will make a plus, so we'll have r times 1 plus 1 over, not 1 over, e to the t times 1 minus p over 1 minus e to the t times 1 minus p. It's a lot of words. Yes. How is what? No, the derivative of L and P is 0. Derivative of T is 1. There's a T in there too, right? Yeah. Derivative of that, you're right. Derivative of natural log of p is just 0 because the p doesn't have any t's in it. There's no t's in that first term. How do we use this to find the mean now? What do we plug in for t? 0, right? Well, certainly on top, we just get 1 minus p, don't we? We put in 0 for t. E to the 0 is 1, so we just get 1 minus p on top. We agree with that? What do we get on bottom? P. So we get 1 minus the quantity, 1 minus p. So we just get a p on bottom. And this will simplify to, well, I think on the sheet it writes it this way. That'll just simplify to 1 over p. I can split up my 1 minus p over the p, right? You get 1 over p minus a 1, and then your 1s will cancel. What was the mean for the geometric again? 1 over p, wasn't it? There's an r times 1 over p. Think about why this makes sense. Say something on the average happens 20% of the time. So you would expect the first occurrence to happen after the 5th trial, right? You'd expect the second occurrence then, if it happens 20% of the time, you'd expect the second occurrence to happen after 10 trials, and the third one to happen after 15 trials, and so on up the line, right? If it happens 20% of the time, you would expect that the expected value would just get multiplied by the number of successes you're looking for, right? So this should make sense intuitively that the mean turned out to be this way. We'll have a more mathematical reason later in the semester for another reason why this happened this way. But intuitively, it makes sense, right? If you think of a probability of something happening a certain amount of the time, you should expect to see the first one after 5, the second one after 10, the third one after 15, the fourth one after 20, and so on up the line. All right, for variance, we have to do second derivative and plug in 0, right? Now remember, that's after you do the log. That doesn't work if you just have the straight moment generating function, right? Okay. But we already took the log, take the second derivative. I'll still have the r hanging out in front, right? On top, or it's not on top, inside the parentheses, derivative of the 1 will be 0. Here we have to do a quotient rule. That looks like fun. Good news is that the derivatives here are easy. It's a constant times e to the t, right? So you get derivative of the top, which is itself, times the bottom, minus the top times derivative of the bottom. We did derivative of the bottom in the previous step, which is why I just wrote it down again. Bottom squared. I feel like I'm the only one having fun today. Put in 0 now. By the way, I want you to do these types of things on an exam. You're not going to do anything with functions this ugly to do this, right? One of the reasons why I'm doing this is I want you to be able to understand how to use a moment generating function to find mean and variance. That's going to be an exam problem, right? The derivatives will be much simpler than this. I'm not going to make you do nasty derivatives. You had one on the homework, right? That was a e to the bt. That's easy to take a derivative of, right? That's the kind of thing I would want you to take a derivative of. I'm just trying to reinforce these things as we go along. I do have reasons. Hand crank. All right, put in 0. This becomes 1, so this is just 1 minus p. This becomes 1. So the whole thing is just P, right? And we've got 1 minus P and a 1 minus P, don't we? So we've got, my hand really did cramp. I was holding it funky apparently. We've got P times 1 minus P in the first ones. We've got a minus 1 minus P squared, because it was a 1 minus, oh, sorry, it's a plus. Well, 1 minus P and a 1 minus P here. What's on bottom? P squared, right? We agree? What does the top simplify to? Let me let's see if we can figure out a guess. Geometric and negative binomial are related to each other, right? Geometric is a special case of the negative binomial. It's if it's first success, right? R equals 1. What was the variance for your geometric? 1 minus P over P squared. What do you think the numerator might simplify to? 1 minus P. Okay, let's see what it does. You see anything that factors out of the top? 1 minus P. In the first term, we're left with P. In the second term, we're left with 1 minus P. Hey, look at that. That becomes 1, doesn't it? I'm so shocked. So again, I would expect to see, just from what we know so far, I would expect to see the geometric formula for my mean and for my variance if the geometric is a special case of the negative binomial, right? I would expect to see the formula in there, right? What may not necessarily be as expected, especially for the variance, is that I just multiply the variance by R. That's probably unexpected. This one intuitively makes sense, right? We already argued why that one makes sense. You may not believe me, but we argued that, right? You may not believe me, but intuitively this one makes sense. This one you probably don't have an intuitive feel for, and that's okay. I wouldn't expect you to. Okay. But again, it shouldn't be a surprise that that showed up. Okay, all right. Ready to do some problems instead of me talking? Sound like a plan? All right. Let's see if we can do some of these problems, and then we're going to switch over to our last discrete distribution, our last special discrete distribution that we'll talk about before moving into continuous distributions on, is today Tuesday? God, it was a long day yesterday. It was terrible. I had 2 long meetings yesterday. On Thursday. All right. Free throw shooter. Going to shoot till she misses. Well, at least in part A. Probability we're making a free throw is 0.9. What's the probability of having the first miss on the 13th attempt or later? What kind of random variable is this situation in part A? Number of trials until the first miss. So what kind of distribution is that? Geometric, right? So it's geometric. We know then our PMF for our geometric is what? Good. Again, this one shouldn't be too bad to remember what it is, because why? If we're going to go until we have the first success, what had to happen on the previous trials? And not success, right? We had to have failures, right? So we had failures up until the last one. So that one kind of makes sense when we put that together, right? We want the 13th attempt or later, so we want the probability that x is greater than or equal to 13. Right? Should be the second. It should be the second problem in the handout from last time. Yeah, it should be the second problem from the handout from last time. Should be the second problem. Yeah. Okay. This would mean 13 or 14 or 15 or and so on down the line, which is probably hard to compute, right? So instead, we can do this using the complement. Probably let x is less than or equal to 12. Good, right? Because we don't want to count 13 twice. Oops. What's p in this case? 0.9. So 1 minus p is 0.1. So if I write it in summation notations, that's what we would have. All right? X could be 1, X could be 2, X could be 3. X can't be 0, right? Because it's number of...
Yeah. Should be the other way around because we're looking for the first place and making it be
Oh, yes, you should be the other way around. Thank you. Yep, you're right. Thanks. There's another mistake. How many did I have on the homework?
3.5.
3.5? Well, there's 2. It might actually be pretty accurate. That okay? And then you could type all that in your calculator. Sounds like a lot, but you should be able then you have the geometric CDF on your calculator. I'm pretty sure, right? So you can just use that at that point. I would not expect you to type all that in by hand. That's nuts. That's an inefficient use of anyone's time. By the way, a lot of these PMFs are built into Excel too. It's been a while since I looked. I just thought of that though. We will use Excel later for some things. One of the nice, I'll just show you real quick. You don't have to worry about it right this second. One of the nice things about Excel is that if you start typing in a built-in formula, the geometric apparently is not built in here. If you start typing in a formula and it's built in, it'll pop up the list for you. You'll be able to pick it out. Okay. Doesn't look like geometric is in there. However, I know binomial is. So there's binomial distribution. Okay. When you put that in, oops, and not hit enter, but hit tab. Okay. It's hard to see because it's so small on the screen. But in your binomial distribution, you can put the number of successes that you're looking for, total number of trials, what the probability of success is, and then you can tell it whether or not it's cumulative. So if you just want to plug it into PMF, you say false. If you want it to be up until a certain point, then you say true. And Excel will do that as well. One of the reasons why I'm mentioning this is because knowing how Excel works in lots of different areas is exceptionally helpful for computations. You've got a nice, gigantic calculator. If you can use it for things that you should use it for, then you should absolutely use it. It's a very, very good skill to have to go use Excel. It's the only reason why I'm going to do some other things in here as well when we get to that point. But in any event, binomial distribution is in here. I don't remember if negative binomial is or not. Yep, there it is. Negative binomials in there too. Okay. I don't think your calculators have negative binomial built into it, does it? I don't believe it does. Geometric is, but negative binomial I don't think is. No, okay. So if you wanted to do something with a negative binomial distribution and actually wanted to calculate it, you could do it this way on Excel. You've got the different parameters that you would want to put in here. Number of S's, number of successes. So this would be your X value that you would want to have the number of trials until that number of successes, and then probability of success, and you can do cumulative. That means that I could also do geometric using the negative binomial, right? Which is why Excel, I'm guessing why Excel doesn't have it as a separate function. Because what can I use for number of successes? 1, right? So in this case, we wanted up until the 12th trial, right? We wanted first success. Probability of success was missing in this case was 0.1. And then we would want cumulative, so we would say true. I'll just type it in. And then it gives you the value. Which should match, well, we would do 1 minus then for the final answer, but that should match what you got in your calculator if you did the geometric CDF. Okay. Anyway, like I said, I'll show you things on Excel from time to time because I think it's important to know how to use Excel in certain situations. And sometimes it's faster to type it in Excel than it is on your calculator. Just being honest. Anyway, questions on how we set that problem up. That problem okay? All right. What looks different for part B? Continues shooting until she misses 3. What kind of distribution is that then? Negative binomial, right? So we want the probability that x is equal to what's x equal to in this case? 30. So we have that binomial coefficient. What's going to go on top? 29. And on bottom, 2, right? We want 3 successes and 27 failures. Failure in this case is making a free throw, right? Seems kind of counterintuitive, but failure is making a free throw, so you would have 0.9 to the 27th, and failure is missing, so we'd have 0.1 third. We've actually done problems like this before we even called it a negative binomial distribution, right? We know something had to happen on the last trial, but we could have any arrangement what happened on the previous trials, and that's where that 29 choose 2 comes from. What's that? Oh. All right. This one okay? Yes. Right, but we're looking for a third miss. So missing is our success in this case. We're trying to get to the third miss, so that's why we're using the 0.1. Okay. All right. Do you want to do another problem like this, or are we okay on that idea? You want to do another one? Okay. Let's look at the next one. Actually, this one may not be a great negative binomial anyway, but that's okay. We're going to take apples and weigh them until you find one underweight bag. What kind of distribution is that? If you're going to draw apples, bags of apples at random until you find the first one that's underweight. It's geometric, right? So what's your PMF then for this one?
1 minus b dx minus 1.
Okay, good. And success here is going to be defined as what? Yeah, finding an underweight bag, right? Probability of that happening is 0.04, so we'll have 0.96 to the x minus 1 times 0.04 will be our PMF. Of the 3 questions after the problem, which one is a PMF question directly, A, B, or C? C, good. C is a PMF question directly, right? Because this is exactly 20, which is what the PMF gives us. So for part C, this will just be whatever f of 20 is. The other two are going to involve the CMF. Which one asks a question about the CMF directly? A or B? It's B, isn't it? CMF goes up until a certain point, right? So it says at most 20. Okay. So this is a CMF question here. The reason why I'm asking about that, I guess technically they call it CDF, but I want to call it CMF anyway. The reason why I'm doing this is because when we get to continuous functions on Thursday, continuous distributions on Thursday, a lot of times we're going to want to change the problem into a question about the CDF, the CMF. Okay. CMF, CDF, same thing. Cumulative mass function, cumulative distribution function. Usually we say mass for discrete and distribution for continuous. But the reason why I'm emphasizing this is because we're going to get to that point in the next chapter coming up on Thursday. So part B would be just your probability that x is less than or equal to 20. That's a CDF question. How would you rewrite your part A in order to put it as a CDF question? Good. Good. So notice both A and B you can write in terms of the CDF, but B is a problem that's directly about the CDF, right? Do you agree with that? And then at that point, that's a matter of putting it in your calculator. Either your calculator or Excel, either or. But if you wanted to write it as a summation, this would go, where would your x start if you wanted to do this as a summation? 1, good, because it has to be, you have to have at least one trial to get a success, right? So it'd be 1 to 20, 0.96 to the x minus 1, 0.04 to the first power. That's important to make sure you know where your sums start, right? If it's a binomial, it would start at 0 because you can't have 0 successes in a certain number of trials, right? You can have all failures. But this one has to start at 1 because you're looking for a first success, and you can't have a success unless you've actually done a trial. Questions on that? That's okay with everybody? All right. Well, let's go on to the next section then. Do a little bit of an introduction here before doing some problems. All right. So you'll notice that we must be talking about something referred to as the Poisson distribution. We haven't talked about what that is yet. To give a practical example of why you might want to know something about this particular type of distribution, perhaps you have your a telemarketing company and you want to make sure you have appropriate staff to be able to handle influx of calls, and you know that on average you have a certain number of calls that come in during a certain period. You're going to want to know, well, if I only have, say, 4 people here, what's the chances that they're going to get basically over flooded? Maybe we've got a whole bunch of people calling randomly. What's the chances there are going to be too many, and do I need to have more staff? Kind of an idea. So maybe you've got a staffing problem at a call center. Maybe you've got a staffing problem at a bank. People come in at a certain rate to the bank. You want to make sure you have enough people to handle everybody's line. You don't want a huge line going out the door. Okay. So that's the idea behind a Poisson distribution. Is you've got something happening on average a certain number of times over a time period. That's the idea. So in the book, they give you a definition of what we refer to as an approximate Poisson process. So let's talk about what the characteristics of a Poisson process is. Well, first, it is a process where you've got we're going to count the number of occurrences over a time interval, over some certain interval. Well, I say time interval. It doesn't have to be time. It just needs to be a continuous interval. And we need the following properties. All right. So let's go back and think about the examples that I gave. Didn't word this really well. That's okay. Let's go back to the examples that I gave. If you've got calls coming into a call center, or people walking into a bank, or maybe you've got some manufacturing process making a sheet of metal, and there's flaws every so often that pops out. Well, depending on the process, I suppose. But do you expect one call coming into a call center to affect any other call coming into the call center? Or do you think they should be independent of each other? Probably independent, right? Do you think of one person going into a bank affecting somebody else going to the bank and getting some business done? Probably not. Maybe, but a little bit iffier, right? But you should expect them to be independent. So one thing that we're going to assume happens here is that is the number of occurrences in non-overlapping intervals. I should say subintervals. Are independent. And there should be numbers of occurrences are independent. Okay. We wouldn't expect the number in happening in one subinterval to influence the number of happening in any other occurrences, any other subinterval. So that's one property we're assuming is happening with this process. To get to where our PMF is, why do you think we want independent? What do you think we might want to start using? What requires independence? What kind of trials require independence? Use the word trial on purpose. What's the name we give to the trials where we have success or failure? They're Bernoulli trials, right? We're gonna basically create Bernoulli trials here. Okay. So that's why we want independence. The second part is that the probability of exactly one occurrence in an interval of length h is lambda times h, where lambda is greater than 0. I forgot a word in there. Let's just put it off to the side here. Okay. Let me tell you what I mean by small enough here. I forgot to put the word in there. A word in before interval. Again, think about your call center, your calls coming into a call center, people walking into a bank. If you think about calls coming into a call center and time being continuous, two calls cannot come in at exactly the same time. One has to get there first versus the other, right? If you think about time being continuous and calls being discrete actions, they're not going to happen at literally the exact same time, right? They may be within a half a second of each other or something, but it's not going to be literally the same time. Okay? So what this property says is that I can, and this one and the next one, says that I can chop up my interval small enough to where either there's no occurrence or one occurrence there. That's what we're doing. Okay. The lambda is just kind of some scale. So if lambda is, say, we would expect 3 calls in an hour, and I want to chop it up into minutes, then I would expect on average to be 1/20th of a call per minute kind of idea. It's a scaling thing that I can chop it up into pieces. Right? It'll make more sense when we're doing problems as opposed to the definition, I promise. Okay. Then the last part is that for small enough intervals, the probability of 2 or more occurrences is 0. All right, so this is what we mean by an approximate Poisson process. The reason why we need this approximate process is to help us figure out a PMF for a Poisson distribution. All right. So what we're going to do is we're going to let x count something again. This is a discrete random variable. It's going to count something. We're going to let x count the number of occurrences in some fixed interval. Now, we're going to just say that this interval has length 1. A unit interval. The idea here is, though, that we should be able to scale this unit for different problems. Okay. So whatever this is, maybe it's an hour, maybe it's a day, maybe it's a month, maybe it's some manufacturing process and you're looking for occurrences within 100 feet of something, maybe 100 feet of wire or something like that, some flaws in it. Okay? Doesn't matter. The interval of length 1 just means that we're saying whatever the unit is, it's 1 unit. Okay? So if the unit's a day, it's 1 day. If the unit's an hour, it's 1 hour. All right. Now we're saying that based on whatever the parameter is, whatever that lambda is, I can break up my interval of length 1 into pieces that are small enough where the probability is just that lambda times the length of the interval. That a single occurrence happens, right? Not 2 or more, because that's impossible if we chop it up small enough, right? But if we chop it up small enough, maybe no occurrences happen, but perhaps exactly 1 occurrence happens. And again, if you think about people walking into a bank, but this door is too small, you can't get 2 people to fit through it at the exact same time, right? So somebody has to go in first. So I can cut those time intervals up into where there's somebody walking to a bank, exactly 1 person, or maybe you've cut it up so small that you've got intervals where nobody walks in through the door. Okay, that's what we're doing. All right. To help things out here, we're going to do this by chopping our interval into pieces. Let's divide our interval. Oops. Into n subintervals. Of course, if I do divide something of length 1 into n subintervals, each one will have length 1 over n, so that 1 over n satisfies the small enough condition. By the way, it's not related to this, but what other process do you do in calculus where you chop up an interval into smaller subintervals? What does that start to do? Integration, right? Yeah. And we're going to do that again here when we do continuous distributions on Thursday. Okay. So all we're doing is saying I've chopped up my interval into small enough pieces where if I look at each little subinterval, either one success occurred or no successes occurred. Okay. Now again, from our conditions, we know that the probability of success, where success is one occurrence, something happened, the probability of a success here is lambda over n, right? Remember it said one of the properties was lambda times the length of the interval, right? So the probability of success here is lambda times 1 over n. Now we can think of, and since they're all independent, we can think of this as a binomial distribution, right? So our probability that we have x successes should be approximately, because it's not quite a binomial process, but it should be approximately what? Well, we've got n subintervals. X of them have successes in it. The probability of success is lambda over n. The probability of failure is 1 minus that. The reason why I'm using approximately equal to here is because it's not quite binomial, because I've taken a continuous situation and made it discrete, right? So it's not quite binomial. To change this into something that's continuous, what do you think I want to do at the end? To change something into a discrete subintervals and make it more continuous over the whole thing, what do you think we want to do at the end? Yeah, take it to infinity. Do a limit. Exactly. Great. Calculus. Very good calculus day, isn't it? We've got the series. Now we're doing limits. We've taken some derivatives. We've talked about integrals. It's a great calculus day. It's like all of Calc 1 and 2 all put together. No one cares. Great. Fantastic. Let's let n go to infinity. Let's see what we can do with this limit. This looks like a fun limit to take, doesn't it? All right, let's see if we can do the limit here. All right, we need to break this into pieces. All right, first thing, on bottom we have x factorial times n minus x factorial, certainly, and then I've got an n factorial on top. We agree? This, I'll write this as, what will I write this as? It doesn't matter. I'll write it as lambda to the x over n to the x to start with. And this I'm going to break into two pieces. So far, so ugly. Okay, good. We're going to do some simplifying around here. I'm going to take this x factorial, and I'm just going to set it with the lambda to the x. Mainly because we're not going to do anything with it. Okay? I'm going to put those two pieces together. We're going to do these two pieces together after I do some canceling here in a second. But let's look at these last two pieces. Over here, does this little x change for the limit? No, it's a fixed x, right? Whatever that x happens to be. So I've got a finite number of factors here, right? We agree? Got a finite number of factors there. What does lambda over n go to as n goes to infinity? It goes to 0. So each of those goes to 1, and we're multiplying a finite number of ones together, right? It's important that it's a finite number, because remember 1 to the infinity is an indeterminate form. Okay? It's a finite number of ones. So in particular, this piece goes to 1. Okay? Don't need to do anything with that. Okay? There's part of my limit. So I'm just going to ignore it. I know it goes to 1. I don't need that. Okay? This also has something that it should be something that perhaps you recognize from calc, but let me write it in a different way. You should have talked about this in a calc class. That should be a special limit. Do you recognize what that is? You recognize? What? That's E. Yeah, good. And in particular, if I change this to an R, that exponent goes here. It goes up as an exponent. Okay. So what's this limit right here going to be? Knowing that that happens. If whatever number is here, it's a plus, and whatever is in the numerator goes here as an exponent. What's that going to go to? E to the negative lambda. Good. So that's going to go to e to the negative lambda. So we've calculated 2 of them. Okay. Now again, I said here in a second, I haven't done it yet, but I said here in a second, oh yeah, don't give me my colors. I'm going to combine these 2 pieces together. Do you see any ends in those? No. So I know what that limit is too, don't I? Right? I know what those limit is too, don't I? Okay, cool. All right, so the only thing that we need to figure out then is the rest of the mess. Okay? So to that end, if I look at my n factorial, on the end of it at some point, there's going to be an n minus x factorial that'll cancel there, right? So on top, oh, actually, let me erase this for a sec. I'm just going to pull those pieces out in front that I don't need for my limit anymore. Everything else we've already taken the limit for, right? I'm just going to pull it out in front. Okay. On top, we'll have n times n minus 1 times n minus 2 times n minus x plus 1 on top. And then on bottom, well, before I write the bottom, why did I stop at n minus x plus 1? Well, I've chopped off n minus x, haven't I? Because I've canceled it with this n minus x factorial on top. Before I write the bottom, how many factors are on top? It's x. Yeah, there's x factors on top. How many factors of n are here? X, all right? So we're going to have n times n times n times n. Now again, is x changing or is x fixed? It's fixed. So does this length of factors here ever change? No. As n goes to infinity, what does that limit go to? 1. What does that limit go to? 1. What does that limit go to? 1. We have a bunch of 1s, right? These all go to 1. So there is our PMF for our Poisson random variable. Okay. Just real quick, since I have a minute, just to check that it really is a PMF, x could start at 0 and go to infinity. Does the e to the negative lambda have any x's in it? Nope. So I can pull it out in front. I promised you that we would get another Maclaurin series. Do you recognize what that is the Maclaurin series for? I remember I want to get 1 out of this. So what better it be the Maclaurin series for? I want this to go away. I need this to cancel out. What better it be the Maclaurin series for? E to the x. What's been plugged in for x? Lambda. Yeah, so this is e to the negative lambda times e to the lambda, which gives me 1. Remember that your Maclaurin series for e to the x is just x to the n over n factorial. Okay. All right. We'll do problems with Poisson next time. But we got a lot of calculus in today. It makes me happy. All right. Anyway, have a good one. We'll see you on Thursday. Again, the homework I gave you today is due Thursday. Next Thursday, not this Thursday. Okay. Because we'll finish up Poisson. We'll do some problems with Poisson. And then we will start continuous distributions on Thursday as well. Have a good one.